Today in this video we will discuss Bernoulli's theorem in fluid mechanics. Bernoulli's theorem states that in a steady, ideal flow of an incompressible fluid, the total energy at any point is constant. That total energy consists of pressure energy, kinetic energy, and potential energy per unit weight of the fluid. So now let's discuss some assumptions in Bernoulli's theorem. What are those assumptions? First assumption is fluid should be ideal and incompressible. And the second assumption is the flow must be steady and irrotational. We will derive Bernoulli's equation from Euler equation of motion, in which only pressure force, gravity force, and inertia forces will be considered. So let's take a fluid element whose area is dA, that this cross-section area is dA, and elemental mass of dm. This is at an angle theta degree. In FBD of this elemental diagram, we will show pressure force, that is Fp, gravity force, and inertia force. Pressure force will be P dA from this side and P plus dP multiplied by elemental area dA from this side. And gravity force, that is weight of this element, will act vertically downward mg, but we are taking it at an angle theta, so it will be dmg sine theta. And inertia force as its net acceleration m times a, that is dm times a. So now we write force equation for this element, that is summation of all the forces should be equals to ma, or we can say dm times a, where dm is an elemental mass, that is density times area multiplied by distance, that is the volume of this element. If we consider ds as the length of this element, then ds will be the volume, and volume multiplied by density, that will be the mass of this element dm. Equating all the forces, taking this direction as positive, so this force P times dA, and this in the negative direction minus of P plus dP multiplied by dA, and this gravity force minus dmg sine theta, that is equals to dm times acceleration. This pda and pda will cancel out, and we will left with minus dp dA minus dm g sine theta equals to dm times a. Now we can put the value of dm from this, and we can take these two terms on the right side. It will become dp dA, dm is rho dA ds g sine theta plus rho dA ds times a equals to 0. Here this ds is in this direction, that is at an angle theta, and we can resolve it in vertical direction, that is ds sine theta, which we can take it as dz. And here dA is common in all the terms, we can cancel it out, and our equation will turns into dp plus rho dz g plus rho ds multiplied by acceleration equals to 0. Now this acceleration can be written as in the form of derivative, that is v del v over del s plus del v over del t, if it's a function of space and time, that is dp plus rho g dz plus rho ds v del v over del s plus del v over del t, that is equals to 0. For a steady flow, and this ds term will cancel out, and we will left with dp plus rho g dz plus rho v del v equals to 0. Now we can integrate all these terms. So integration of dp will be pressure P, and integration rho g dz will become rho g h, we can say, or z, and this term integration of rho v dv will become rho as constant, rho v square by 2. and this will become 0 because differentiation of any constant will be 0. So we can write, if we integrate this term, it will be a constant value. If we divide whole term with rho g, it will become p by rho g plus z plus rho v square upon 2g. So if we divide this whole term with rho g, this equation will turn into p by rho g plus z plus v square upon 2g. That will be equals to a constant value, which is our Bernoulli's equation. This is our pressure energy, and this is kinetic energy, and this is potential energy, and this is potential energy. As Bernoulli's theorem states that sum of potential energy, kinetic energy, and as Bernoulli's theorem states that sum of pressure energy, potential energy, and kinetic energy is constant. It's all about Bernoulli's theorem. Thanks for watching.